Hello everyone, welcome to Swag Talks. I am Prasanna from Cybersecurity and my teammate Pranya from Cybersecurity. We made this video under the guidance of Dr. M. Prasad sir, and our topic is about hardware synchronization in operating system. Hardware synchronization refers to the use of hardware level mechanisms and instructions to coordinate and control the execution of concurrent process or threads in a computer system. The primary goal of hardware synchronization is to ensure the correct and orderly access to shared resources, such as memory locations or critical sections of code, in a multi-core or multiprocessor environment. This coordination is essential to prevent data corruption and race conditions and other concurrency related issues that may arise when multiple components attempt to access shared resources simultaneously. Key components of hardware synchronization include atomic operations, memory barriers, and synchronization primitives like locks, mutexes, and semaphores. These mechanisms rely on low level hardware instructions to provide guarantees of atomicity and enforce the proper ordering of memory operations, ensuring that critical sections of code are executed without interference from other concurrently running processes. Hardware synchronization involves the use of hardware level features and instructions to manage and control the concurrent access to shared resources, maintaining the integrity and consistency of data in a multiprocessing or multi-core computing environment. Here are some common hardware synchronization mechanisms used in operating system. The first one is atomic operations. Atomic operations are fundamental building blocks for hardware synchronization. An operation is considered atomic if it appears to occur instantaneously without any possibility of interference from other operations. In multi-core or multi-process systems, atomic instructions guarantee that a particular operation will be carried out without interruption. Next one is memory barriers. Memory barriers are also known as memory fences, are instructions that enforce an ordering constraint on memory operations. They ensure that certain memory operations complete before other begins. Memory barriers are crucial for preventing the reordering of instructions by the compiler or the hardware, which could lead to unexpected results in a concurrent environment. The next one is locks. Locks are synchronization primitives that prevent multiple threads or processes from simultaneously accessing a shared resource. Hardware support for locks often involves atomic operations like test and set or compare and swap. When a thread wants to access a shared resource, it acquires a lock, and other threads must wait until the lock is released. The next one is compare and swap, called CAS. CAS is an atomic instruction commonly used in hardware synchronization. It involves three operands: a memory location, an expected value, and a new value. The instruction atomically compares the current value at the specified memory location with the expected value. If they match, the new value is written to the memory location, otherwise the operation fails. CAS is frequently employed in implementing lock-free data structures. The next one is mutexes and semaphores. Mutexes and semaphores are higher level abstractions built on top of atomic operations and locks. Mutexes provide exclusive access to a resource, while semaphores can be used to control access to a resource with a specified number of permits. And the next one is memory consistency models. Hardware synchronization is closely tied to the memory consistency model, which defines the order in which reads and writes to shared memory locations become visible to different threads or processes. Different architectures may have different memory consistency models, influencing how synchronization primitives need to be used to ensure correct behavior. The next one is transactional memory. Transactional memory is an advanced hardware synchronization concept that allows multiple threads to execute a sequence of instructions as a single atomic transaction. If a conflict occurs, the transaction is rolled back and retried. Now let us know about test and set instruction. The test and set instruction is a fundamental atomic operation used in hardware synchronization to implement locks and manage access to shared resources in a concurrent computing environment. It is a simple and powerful instruction that provides atomicity, meaning that operation is indivisible and can be interrupted by the other operations. The basic idea behind the test and set is to atomically read the current value of a memory location and set it to a new value, and typically one in a single uninterruptible operation. Here, how test and set instruction typically works: read the current value and set a new value and return the previous value. The key characteristic of test and set is that these steps are performed atomically. This atomicity is crucial in the context of synchronization because it allows multiple threads or process to use the test and set instruction to contend for a lock without the risk of interference. By checking the value before setting it, a thread can determine whether the lock was already held by another thread. While test and set is a powerful primitive for building synchronization constructs, it is worth noting that modern hardware often provides more sophisticated atomic operations like compare and swap and fetch and add, which can be used in conjunction with other techniques or more efficient and flexible synchronization. Here is the condition for the test and set instruction and mutual exclusion with test and set instruction. Now let us know about compare and swap. CAS is an atomic operation provided by many CPUs. This means that the operation is guaranteed to complete without interference from other threads or process. CAS allows a thread to check if a memory location still has the expected value. If so, update it to a new value. That is useful for implementing synchronization primitives, which are tools for coordinating access to shared resources. For example, CAS can be used to implement lock-free data structures, which allow multiple threads to access some data without causing conflicts.
And coming to the comparison of different testing techniques, there are some of the common testing techniques in hardware synchronization. Unit testing, it mainly focuses on individual components or modules such as atomic instructions or synchronization primitives. Pros of this unit testing is nothing but isolates and tests specific functionalities allowed for targeted verification. And it cons is may not capture interactions between different components or the overall system behavior. And another testing technique is integration technique. It mainly focuses on interaction between different components or modules, ensuring they work together as intended. Pros of this integration testing is validates the collaboration of components, detecting issues that may arise when your different synchronization mechanisms are used together. And cons of this integration testing is does not necessarily accesses the complete system behavior or performance. Concurrency testing, it focuses on accessing the system's behavior under concurrent execution of multiple threads. Pros of this testing is identifies race conditions, deadlocks, and other concurrency related issues. And cons of this concurrency testing is complexity increases with the number of threads and possible interleavings. And the hardware synchronization has a great impact on system performance is a critical consideration in designing concurrent and parallel systems. Hardware synchronization mechanisms are essential for ensuring the correctness of concurrent programs, but they can also introduce overhead and affect performance. Here some key factors to consider. They are contentation and scalability. Its a great impact is excessive use of locks or other synchronization primitives can lead to contention, where multiple threads contend for the same resource, causing delays and performance degradation. And another impact is locking overhead. It impacts example locks such as mutexes or semaphores introduce overhead, especially when contention is high. Lock execution and release operations involve atomic instructions and can be relatively expensive. Certainly, we have learned about the impacts of hardware synchronization in system performance. But keeping those challenges aside, we can come with solution for those. The first solution for the contention problem is using fine grained looking where locks are applied to smaller sections of data to reduce contention. Alternatively, explore lock-free and wait-free algorithms to allow threads to make progress even in the presence of contention. For this, and the solution for lock overhead is minimize lock usage whenever wherever possible. Consider alternative synchronization mechanisms such as reader writer locks or optimistic concurrency control methods like transactional memory to reduce lock overhead. And solution for the atomic operations is using atomic operations judiciously. Choose the appropriate atomic instruction, example compare and swap, based on the specific requirements of the synchronization task. Consider lock-free or wait-free algorithms for scenarios where atomic operations become a bottleneck. And the solution for memory barriers is using carefully memory barriers to achieve the necessary ordering without introducing unnecessary delays. Understand the memory consistency, model, and tailor the use of memory barriers accordingly. Conclusion. As we wrap up our journey through hardware synchronization, let's recap the key points discussed. One thing you have to remember is efficient hardware synchronization is the key to achieving efficient and reliable parallel processing. Embrace the power of synchronization and unlock endless possibilities. Thank you.